My name is Alejandro. I am a PhD student. I'm doing my PhD research at Minos Group, the University of Rovira Virgili, and I want to show you here development of a wearable wireless sensor network for air quality monitoring. So I will briefly give you a short introduction, the objective, and the results that I have, and then the next steps. For sure, everyone in this room knows about the importance of the air quality monitoring due to the increasing of the air pollution. But just for giving you a few statistics, here I am showing you the risk factor of death. So air pollution is the third one. And another number is like the air pollution contributes more than 11% of the death globally. We have this in one hand. On the other hand, we have like an increase of the devices connected to the Internet of Things. And we have an expectation in 7 years that we will have like more than 29 billion of devices. So in that order, we start to think of develop our own system to interface the sensor that we develop in our research group. So we start thinking that this the electronic design and the system should be like really reconfigurable, and the nodes needs to be like really easy to integrate in the network application. So here I am showing you this block diagram, really simple one, in which I am presenting you a few sensor nodes connecting, interfacing a hotspot through wireless fidelity, and they are getting the path to the information that they are sending are traveling through wireless to a server in which is running a MQTT broker, which is a protocol like really gets the life easy for people who are developing a lot of nodes, and they are trying to send the information to the same point or server or database. So also this system that I am going to present to you, it has like a testing user interface. So in this testing user interface, we are just going to show you the variation of the signal output of the sensor, and then the heater, the current through the heater to the sensor. So here in this area, I will describe you here the sensor that we work in our group. This type of sensor are based on alumina substrate, and at the front view, they have like interdigitate electrode with the sensing material, and in the bottom view, the sensor has a heating element. So we can heat the sensor to get to the rightful level of temperature, and then acquire the change of the conductivity of the sensor when reacted with some target gas. So in this manner, in the right part of the slide, I'm showing you the final design that we made for one of this node, and I will give you a few insights about it. First, in the middle, we can see here a general block diagram for this for the electronic. The electronic have been thought like to be really reconfigurable and adaptive to different type of sensors, chemo-resistive sensors. But as you know, this type of sensor can have different baselines and can then react with different response. I'm talking about the amplitude of the response. So when biasing the sensor, you need to make really sure that you are making rightful biasing of this type of sensors. So in the first step, we have developed a control algorithm to change this biasing of the sensor according to the baseline of the sensor that you can connect there. So secondly, we can change dynamically the resolution of the measurement by changing the gain of the acquisition channel that we are connecting between the output sensor and the microcontroller. So next, we have also controlling the current that we are passing through the heater in order to completely have the control about the current that we are making there. And of course, we have the calibration curve related to the temperature and the current through that heater. And since we have this extremely control of that current, we can also make some temperature modulation and put some different waveform if it is needed to get the better response of the sensor. Another algorithm that we have developed is related to, for example, there is a power cut in a device. So we have all the startup configuration on the device stored in the non-volatile memory, the micro SD card. So when the device starts up, all this configuration of the hardware is uploaded from the SD card, and then all the hardware is configured. But for example, if the algorithms that change the bias of the sensor because the baseline is changed, somehow the bias of the configuration of the hardware change, in that moment, the software also will be store this configuration in the micro SD, just in case a power cut exists, and then when the power goes on again, the board will be restart all the configuration of the hardware just in the same point that was before the power cut. Also, another algorithm that we have is a connection cut. In case the wireless connectivity is completely off, all the data from the sensor will be stored in the micro SD. And when the connection is on again, we will start multiplexing the data from the sensor and the data from the SD card through the server application. So another thing that we have think of is a control of an actuator. What I'm saying with this, that we can control, for example, a fan or a bomb, if we can redirect the flow of the gas directly to the sensor. In that matter, in that picture that I'm showing you there, it's not connected any fan, but we have this feature of the board. Also, at the bottom of the image in the right, we have connected some specific connector to interface this type of sensor that we are working with in our group. Here in this slide, I am just want to show you one of the housing that we are proposing for this board. As you can see, the mechanical design has some gaps, some holes in which the sensor can be connected and can be react to the gas by diffusion. And for example, another type of connector could be the one in the middle that we did just before came here to have that picture of the laptop. We just connected the board to a chamber in our gas room and then placed 4 sensors of tungsten trioxide and repeatedly did some pulses of 1 ppm of NO2. So we can have the data showing in that slide that is just simply the resistance of the change of the resistance of the sensor. And then also we are presenting the current through the heater. So in that sense, we think that we have an electronically really robust and reconfigurable, and it's completely finished in my opinion. And then we can adapt that having a new design respect of the mechanical part to focus that electronic and the nodes directly to an application. So in the next step, we are developing an algorithm to do some regression algorithm to classify it and quantify the gases, but this is extremely tied to the sensor that we connected in the board. So that's it. I just wanted to show you this design. It's extremely easy to connect new nodes. So far, we have fabricated 5, and they work extremely perfectly in the test that we have done at the moment. That's it. Thank you so much for listening to me, and I will be more than happy to answer any question.